we have Fenil Doshi, who will be telling from Harvard, who will be telling us about human-like signatures of contour integration in deep neural networks.
Hi, everyone. My name is Fenil, and yeah, I'll be speaking about human-like signatures of contour integration in deep nets. So when pattern light falls onto the retina, it passes through a series of cortical stages to arrive at a meaningful percept of the world. And in many ways, these deep convolutional neural networks have emerged as these de facto models of visual processing. They're able to do behavioral tasks like object recognition with human level accuracies, but at the same time, their intermediate learned feature spaces do predict significant amount of variance in the neural responses to object stimuli. But now there are recent studies that have shown that these models are just way too texture biased. And as a result, they lack the mechanisms and representations that are necessary to extract the global shape of objects. On the other side, contour integration are these early mechanisms thought to be these initially critical steps in root this global shape representations. And these mechanisms are able to group and link nearby contour elements that are similar in nature to give us these continuous edge-based representations that from where we can further extract global shape and global form. Let's try to highlight this phenomena using a demonstration using stimuli generated by Field and colleagues. So after I'll show you this gray display, another display will be shown where a bunch of Gabor elements will be systematically situated along a continuous contour. And in addition to these contour elements, there will also be these background elements, which are also Gabors and just randomly situated on the gray screen. And I want you to clap as soon as you notice that extended contour when you look at this image. So everyone ready? Okay, that's the first demo. Awesome. So I guess everyone was able to identify this contour, right? This was an easy image. Let's try another example. Yeah, this was a bit harder one, but this is where the contour is hidden inside the image. And for these two images that you saw, they differed in terms of their contour by controlling for their curvature. So this beta parameter is able to control how curvilinear the contour path is going to be. So if we start with a beta, which is small, we see a relatively straight contour. And as we increase beta, we start seeing these contours which are increasingly curvilinear. And what Field and colleagues found was that as the curvature increases, there's a systematic drop-off for humans to detect the presence of a contour. And in light with this behavior, multiple mechanisms and models were proposed that can account for this. So one plausible explanation is that we have these association fields early on in the visual system, which are these extra classical receptive fields with constraints based on orientation and position. And they're probably realized in the brain through some kind of lateral connections. Another suggestion was that this is happening through some kind of visual interpolation. And a completely different explanation was through these temporally synchronized oscillations, which can segregate different objects in the scene. On the modeling side, there were these bottom-up second-order filtering strategies. And like we just saw in the last slide, last presentation, there are these recurrent neural networks with top-down and horizontal connections that can do these perceptually grouping tasks. Now, standard convolutional neural networks have none of the specialized machinery that is explicitly baked inside them. So no association fields, no synchronized oscillations, no recurrent networks. So does that mean that these models are just architecturally incapacitated to do any kind of perceptual grouping? And that brings us to the first question that we asked over here. If these CNNs can even do some contour integration or not. Now, if they do they do it in a human-like way? And if not, can we use them as a test bed to really understand what we might want to add to incorporate these mechanisms? To answer the first question, we first test if contour integration is even possible using object recognition features. So we take an AlexNet trained on ImageNet to do a 1,000-way object categorization. And we show this AlexNet a bunch of images with all these Gabor elements similar to the displays that you just saw before. And there are two types of images in this data set. One, a contour image, where a subset of the Gabor elements will fall along an extended contour. And two, the second one will be the no contour image, where all the Gabor elements are just randomly positioned on the gray screen. In the architecture, we remove the fully connected layer, plug in a linear readout, which can detect the presence or absence of a contour, and we'll freeze the convolutional layer. After doing this, we're going to train the linear readout to detect the presence of a contour. And we call this the object recognition AlexNet. This is because it tests how sufficiently good the object recognition features are to detect the presence of a contour. So on training this model, it achieves an accuracy of 67%, which is above chance. But if the model would have been architecturally incapacitated, then this is probably the best the model can get. To test that, we then try to train all the features underlying the architecture of the model itself. So rather than freezing the convolutional layer, we just allow all the layers of the model, and including the linear readout, to get trained. And we call this the fine-tuned AlexNet. On training this model, it achieves an accuracy of 91%, which is way above the chance accuracy that we would have expected if it was architecturally incapacitated. So it's doing the task right. But we try to dig deeper to explore the strategies that these models are leveraging to do these tasks. So for instance, when a model like this looks at an image and predicts that the contour is present, is it really looking at those elements that fall along the contour path, or something completely random, something from the background elements? So we use guided backpropagation to explore where the models look at by getting gradients with respect to its output prediction and propagating it back to the pixel space. And we do this both for our object recognition AlexNet and our fine-tuned AlexNet. So for instance, when these models look at this image, this is where these models are going to look at to predict the presence of a contour. And specifically, these are the attention-based saliency maps. When we do that for a bunch of images, we quickly notice that these fine-tuned AlexNet is probably picking up on the right data. It's actually looking at those contour elements and separating it from the background. We verify this using something called contour saliency scores. So for every image that these models are looking at, we also know the exact position of the elements that fall along the contour path and the background elements. So using this, we can get the average saliency for the path and the average saliency of the background. And together, this gives us the contour saliency, which is the mean absolute difference between the two. When we look at the score, which ranges from 0 to 1, we see that the fine-tuned AlexNet is picking up on the right information. It's able to segregate the contour elements and link them on as though it's lying on a common contour to make its prediction. So to answer the first question, yeah, these models can really do contour integration, and they're not architecturally incapacitated. To answer the next question, which is, if it's doing it, is it really doing it in a human-like way? We get back to the human data where we see that there was a systematic drop-off as the curvature, which is this beta value, increases. These models were just too good. They didn't have that systematic drop-off. And one reason why this was happening is because, again, to separate out, while they're separating out the path elements to get the contour, that's really not dependent on the curvature. So yeah, these models are able to do the task. They're doing it good. They're doing it with the strategy we wanted to, but they're still not human-like in nature. So we come to the third question, that if it's not human-like, what do we really need to add to incorporate these mechanisms? And looking at the human behavioral data, we hypothesize that probably tuning these models to contours of low curvature might do the task. So rather than fine-tuning them on images which have a broad curvature, which originally ranged from 0 to 75 degrees, we just train these models on images with specific curvature values. So 0 degrees, 15, 30, 45, 60, and 75. And when we did that, what became evident was when the models were trained on these contours with low curvature, they had the drop-off compared to the scenario when the models were trained on contours with higher curvature. And in addition to that, this model, which was trained specifically on orientation of 30 degree, actually fell in the human range. Now, was this about something about 30 degree or something around 30 degree was still an open question. So we tested that by fine-tuning additional models on curvatures around 30 degrees. So plus minus 5, plus minus 10, and plus minus 15. And we saw that this model that was trained specifically on curvatures of 30 plus minus 10 degrees really was the sweet spot. So when we trained the model on 20 degrees or 40 degrees of orientation, they didn't fall in the human range. When we trained it on windows of more than 10 degrees, so something like 15 degrees, they fell outside the range. So there's something about this 30 plus minus 10 degrees that's doing some magic. And here we saw its sensitivity to this beta parameter, which is the curvature of the path, but there were additional parameters that were used to generate all those stimuli. For example, there was this alpha parameter, which controlled how locally aligned those discrete Gabor elements were with respect to the continuous contour. So here is an example. If you look at this contour, and if you focus on this Gabor, we can change alpha, which will kind of change its alignment with respect to the contour. So for the humans, when alpha was 0, so when everything was aligned, we saw that there was a drop off as curvature increased. But in addition to that, as alpha increased, this task just got increasingly harder for humans. And the model that best captured the human behavior when alpha was 0 was also able to capture behavior when alpha was 15 and 30. It had that systematic drop off. It's also important to note that this model was only trained on images when alpha was 0, when everything was aligned. So this phenomenon of capturing when alpha was 15 and 30 just naturally fell out of this model. So probably, at least from all this data, we probably said that to make this human-like, we probably need to specialize them to contours with orientation of 30 plus minus 10 degrees. And just to summarize all these findings, first we saw that feed-forward CNNs can do contour integration by successively segregating and linking those contour elements. So it's picking up on the right information. But when we tune them to curvatures which are from 0 to 75 degrees, so through a broad curvature range, they're not human-like in nature. But only when we tune them to curvatures of around 30 degree, plus minus 10, they do capture multiple aspects of the phenomena. And this targeted range of orientation places some interesting constraints on the kind of neural circuits we ourselves might be using to do these contour integration tasks. So are we like systematically tuned and biased to some specific kind of orientation? And whether this is picked up through visual experience from natural image statistics, that's an open question. That's what this model generates an hypothesis about. And on the deep net side, in light with the previous studies, we showed that while object recognition did not provide the sufficient inductive bias to allow these models to start seeing shape, probably allowing these models to do these contour integration tasks might add a bottleneck to learn the representations that are necessary to later see shape. And with that, I'd like to thank you.
3 minutes for questions.
Hi, thank you very much for your interesting talk. I actually wanted to ask you whether you tried the distances, did you try like different distances between these Gabor filters?
Yeah, so this is what we're right now currently working on, where we are trying to first map on the analytical receptive field of the CNN layers itself, like at different layers. And then we're kind of controlling and changing that distance, which is also what in the psychophysics study, they changed the distance and they saw that that did not matter. So we're trying to test that phenomenon right now on the deep nets.
And the second question is that, do you think we can come up with like a CNN architecture, for example, like an hourglass architecture that can do can use like prior information and not be tuned on big set of images to do this task of contour integration?
So so one plausible suggestion is to have like these lateral connections, which is possibly going to allow it to look at different curvature values, and which is also similar to the association field model. So I think like one prior thing which we could do is either have these transformers which already have fully connected layers in the beginning, which can probably attend to like different parts together, or explicitly like build these lateral connections that might do these things like in terms of prior architectures.
Thank you. Thank you very much.
Hi, Fenil. Really cool talk.
Thanks, Nick.
So have you, I was like just about to ask this question, then you showed the thing at the end where you're asking whether this is going to change our view of, object recognition in these networks. Have you tried training these same networks to do contour integration and object recognition at the same time, and do they compete with each other?
Yeah, so right now, for these models, object recognition is not a good predecessor, but what we are trying to test right now is two things. First, if we can use these contour integration as a regularizer, so using them as additional tasks. But the second thing is we're also trying to test systematically how much of representations do we really need to store. So how much do we need to fix from contour integration, and then like how much do we need to change to do these object recognition tasks. So yeah, that's what we're working on right now. Thanks, Nick. Yeah.
Thanks for the nice talk. So in the first part of your talk, you showed us that like you trained a linear readout from the last conv layer of AlexNet to get 67% on your contour task. Have you tried doing a linear readout on like the first one or two layers, like the first couple of conv layers? Like what's the accuracy for those?
Yeah, we haven't tried the first convolutional layers. We've tried it for like all the layers after the convolutional layers have been like processed. So we tried for FC6, FC7, and then the first one after average pool. But we haven't tried. We should probably be trying it for the first convolutional layer.
Okay, cool, thanks.
Thank you.
Thank you.